Alright, let's go. Number 10. The Bloop. In the summer of 1997, oceanographers at the National Oceanic and Atmospheric Administration were doing what had become routine work, sifting through the Equatorial Pacific Ocean Autonomous Hydrophone Array. The array itself was a repurposed Cold War asset, part of the Navy's SOSUS network built in the 1950s to track Soviet submarines. By the mid-90s, civilian researchers were using it to eavesdrop on whale migrations and undersea volcanoes. The rules of the ocean were well known. Whale calls have signatures. Blue whales sit around 10 to 40 hertz. Fin whales cluster near 20 hertz. Ship engines, seismic events, icequakes, each leaves a distinct acoustic fingerprint. Anything unclassified gets a name and a folder, and eventually a mechanism. Then a signal arrived that broke the folder system entirely. Christopher Fox at NOAA's Pacific Marine Environmental Laboratory in Newport, Oregon, cataloged the event in the late 1990s. The waveform swept down from roughly 50 hertz over about a minute. The sensors that caught it were spaced over 5,000 kilometers apart in the South Pacific, near the coordinates 50 degrees south, 100 degrees west. It sounded, to Fox's own description, like something alive, and it was louder than any known animal. Whale was the first explanation. The audio profile matched a biological source, but no living creature produces sound at that amplitude. A blue whale. The loudest confirmed animal would have had to be several times its size. A Soviet submarine was ruled out, the signature was wrong, and the Cold War was over. Volcanic activity was proposed, but no matching seismic events registered. Giant squid was floated in popular press and quietly discarded by acousticians. Cephalopods have no gas-filled resonating organs. In 2012, Robert Ziak and colleagues at NOAA suggested icequakes from Antarctic ice shelf calving as the source, and the case was declared closed by most researchers. But the mechanism that made an icequake sound biological has never been fully resolved. Which means, for 15 years, a natural process on our own planet was masquerading as a creature. How many other creatures are still filed in those archives? The Bloop had a source we could point to. The next entry does not. Number 9. The Taos hum. In 1993, a small group of residents in Taos, New Mexico began complaining to the local health department about a low, persistent humming sound. Not tinnitus. Not their appliances. A hum that seemed to come from outside their houses, from the ground, from the air. The complaints reached Congress. Congress asked the University of New Mexico to investigate. The setup here is straightforward. A sound is either present in the physical environment or it is not. If it is present, a microphone should capture it. If it is not, the perception is neurological. Physics recognizes no third category. The Taos hum refused to sit in either. Joe Mullins, an engineering professor at the University of New Mexico, led the 1993 investigation with a team of acousticians from Los Alamos National Laboratory and Sandia National Laboratories. They deployed sensitive microphones and seismographs across the affected homes. In the technical report submitted to Congress the following year, they documented that some residents could reliably identify when the hum was present, but the instruments recorded no corresponding acoustic signal above the noise floor. Roughly 2% of the local population reported hearing it. Every proposed source was tested. Military communication systems, including the Navy's extremely low-frequency transmitters used to reach submerged submarines, were checked and cleared. Industrial equipment in the region was audited. Tinnitus was ruled out by the correlation between different hearers noticing the same on-off cycles. Otoacoustic emissions from the inner ear itself, sounds the cochlea generates spontaneously, were considered, but the frequencies didn't match consistently. David Deming, a geophysicist at the University of Oklahoma, published a 2004 paper in the Journal of Scientific Exploration reviewing similar reports from Bristol, Windsor, Auckland, and elsewhere. No unifying source emerged. The implication is unsettling in a very specific way. Either a very small subset of humans has hearing that reaches into a physical signal the rest of us cannot detect, meaning our instruments and our anatomy are both incomplete. or the sound is being generated inside the head of the listener with an on-off pattern synchronized to something outside it. Neither answer is comfortable. What is the shared clock? That's a sound the world argues about. This next one, no one argues about, they just can't explain it. Number 8. Sonoluminescence. In 1934, two researchers at the University of Cologne, H. Frenzel and H. Schultes, were working on Sonar. They wanted to accelerate photographic development by exposing film to intense ultrasonic waves in a water bath. When they developed the film, they found unexpected spots of exposure. Something in the water was emitting light. The standard rule is simple. Sound is a mechanical pressure wave. Light is electromagnetic radiation. Converting one to the other requires an energy pathway, a hot filament, a chemical reaction, an electrical transition. Sound waves passing through room temperature water should not spontaneously produce photons. Sound waves passing through room temperature water do produce photons. The clean version of the effect was isolated in 1989 by Felipe Gaitan, then a graduate student under Lawrence Crum at the University of Mississippi. A single air bubble suspended in a flask of water, driven by an acoustic standing wave at around 26 kilohertz, collapses and re-expands thousands of times per second. On each collapse, it emits a flash of light lasting roughly 100 picoseconds. Seth Putterman's group at UCLA published extensively on this through the 1990s and 2000s in physical review letters. The bubble collapses to about 1 micron. Temperatures inside are estimated at around 20,000 Kelvin, hotter than the surface of the sun. The explanations have accumulated and failed. Black-body radiation from a hot compressed gas is close, but doesn't fit the emission spectrum precisely. Bremsstrahlung from ionized plasma inside the bubble is a partial fit. Julian Schwinger, before his death, proposed that the effect was quantum vacuum radiation, photons pulled from empty space by rapid boundary movement, the dynamical Casimir effect. That interpretation remains contested. The detailed physics of the collapse, how a millimeter-scale bubble compresses matter to conditions approaching stellar cores, is still not fully modeled, which means every ultrasound machine used in a hospital is operating next to a physical process we cannot fully write down. What temperature does the bubble actually reach at its center? From bubbles in a beaker to voices we cannot hear. Number 7. Infrasound animal communication. In 1984, Katie Payne, a bioacoustician at Cornell University, was standing in front of the Asian elephant enclosure at the Washington Park Zoo in Portland. She noticed a throbbing sensation in the air, not a sound exactly, but a pressure. She and her colleagues brought recording equipment and captured what turned out to be elephant vocalizations below the range of human hearing. The standard assumption before this was that large land mammals communicated in ranges we could detect. Zookeepers had worked with elephants for over a century. No one had documented systematic infrasound use. Payne, with William Langbauer and Elizabeth Thomas, published in Behavioral Ecology and Sociobiology in 1986, documenting elephant calls at frequencies between roughly 14 and 24 Hz, below the standard 20 Hz lower bound of human hearing. Subsequent fieldwork in Namibia and Kenya demonstrated that these calls travel several kilometers through air and possibly farther through ground. Blue whales, studied extensively by Roger Payne, Katie Payne's former husband, produce calls at source levels reaching 188 decibels underwater, propagating potentially thousands of kilometers through deep ocean sound channels. The failure parade here is not about explaining the physics. Infrasound propagation is well modeled. It is about decoding the content. Every attempt to build a comprehensive elephant lexicon has produced partial vocabularies at best. Joyce Poole's Elephant Voices project has cataloged over 100 distinct call types, but the syntactic structure, whether elephants combine calls into anything resembling sentences, remains open. Cetacean researchers have made similar limited progress with whale song despite 50 years of recordings. The implication is that two of the largest and most intelligent groups of animals on Earth have been holding continuous long-distance conversations for the entire span of human civilization. We have been standing next to them, unable to hear a single word. What are they saying about us? sound we cannot hear, now sound that can pick things up. Number 6. Acoustic levitation. In 1933, physicists Carl Bix and Hans Miller at the Technische Hochschule in Aachen were investigating standing waves in ultrasonic fields. They noticed that small droplets suspended in the wave field held their position against gravity. The observation was catalogued and largely set aside for decades. The rule that seemed to be under threat is not mysterious. Standing pressure waves create nodes and antinodes, a small object of the right density considered a pressure node where forces balance. The physics itself is classical acoustics. The strange part is not that it works. The strange part is what it can do. Modern arrays have pushed the effect into territory that engineers a century ago would not have believed. Asier Marzo, then at the University of Bristol, published a paper in Nature Communications in 2015 describing acoustic tractor beams, configurations of ultrasonic transducers, typically operating around 40 kHz, capable of pulling, pushing, and rotating small objects in three-dimensional space using sound alone. Marzo's later work at the Public University of Navarre in Spain, along with groups led by Bruce Drinkwater at Bristol and Kai Meld at the Max Planck Institute, has demonstrated multi-object manipulation, contactless handling of pharmaceuticals, and drop-on-demand chemistry. The failure of prior imagination is documented in the engineering literature itself. Reviews in physics of fluids and applied physics reviews note that the theoretical framework for what could be lifted and how precisely was developed by Louis King in 1934, but the assumption for decades was that the effect was a laboratory curiosity. It is now being seriously studied for pharmaceutical manufacturing, where contact with surfaces contaminates the product, which means the air around you, given the right pressure field, can be made to hold objects. The vacuum you assumed the atmosphere was, empty space you move through, is a medium that can be sculpted. What else can be lifted if the frequency is right? Sound that holds objects. Now sound that holds notes that were never played. Number 5. The missing fundamental illusion. August Seebeck, a German physicist working in the 1840s at the Technical University of Dresden, was investigating perception of pitch using a rotating siren disk. He noticed something that contradicted the accepted theory of hearing at the time. His listeners reported hearing a pitch corresponding to a frequency that was not physically present in the signal. Hearing was thought to work by direct frequency detection. The cochlea, developed later in Hermann von Helmholtz's 19th century work, was modeled as a set of tuned resonators. If a frequency is not physically present in the sound wave hitting the eardrum, no resonator should respond. And no pitch at that frequency should be heard. The listeners heard it anyway. Andrew Oxenham and colleagues at the University of Minnesota published a paper in Proceedings of the National Academy of Sciences in 2011 demonstrating that the auditory cortex reconstructs the missing fundamental pitch from the pattern of harmonics present, even when the fundamental has been completely filtered out. Josh McDermott's laboratory at MIT has extended this work using functional MRI to map the regions of the auditory cortex involved. The reconstruction happens in the brain, not the ear. The failure parade is where hearing theory has spent 180 years. Pure resonance theory could not account for it. Place theory, the idea that pitch corresponds to which point on the basilar membrane is stimulated, cannot fully explain it either because the relevant location on the membrane is not being stimulated. Temporal theories, which look at the timing pattern of neural firing, do better but do not fully close the loop. Predictive coding models proposed by Carl Friston and others suggest the brain is filling in what it expects to hear, which means every telephone conversation you have had where the fundamental frequency of a human voice is cut off by the compression has involved your brain generating a pitch that was never in the signal. How much of what you have heard your whole life was actually there? The brain hears sounds that don't exist. Now the universe makes sounds we assumed were impossible. Number 4. Plasma waves through interstellar space. In August 2012, the Voyager 1 spacecraft, launched in 1977 to study the outer planets, then repurposed for interstellar mission, crossed what mission scientists came to call the heliopause. The team at NASA's Jet Propulsion Laboratory, led by Don Gurnett at the University of Iowa, was monitoring the plasma wave instrument aboard the craft. The instrument had been designed decades earlier to measure oscillations in ionized gas. The rule from every physics textbook is that sound requires a medium of atoms or molecules dense enough to propagate mechanical waves. Interstellar space with roughly 1 atom per cubic centimeter was described as effectively silent. In space, no one can hear you scream. This was not marketing. It was accurate. Then Voyager's instrument registered oscillations in the interstellar plasma at frequencies between about 2.3 and 3.5 kilohertz. Gurnett's team published the detection in Science in 2013. When the raw plasma density oscillations are shifted into the audible range, they produce a rising tone. This is not sound in the strict mechanical sense. It is a longitudinal wave in the ionized medium of the interstellar plasma, driven by disturbances from solar coronal mass ejections propagating outward. The distinction matters technically. The plasma frequency is a real, measurable oscillation of the medium related to the local electron density. The failure of the popular assumption is the interesting part. For decades, space is silent was taught as a hard rule. It is a hard rule for sound as conventionally defined. It is not a rule for pressure waves in ionized gas, and interstellar space, it turns out, is filled with such waves, from the solar wind, from supernova remnants, from the galactic magnetic field. The Perseus cluster of galaxies has been generating a pressure wave corresponding to a B-flat approximately 57 octaves below middle C for at least 2.5 billion years, according to Andrew Fabian's group at the University of Cambridge, working with Chandra X-ray observations published in 2003. Which means the sky above you, the vacuum you were told was silent, has been ringing for billions of years. What note is the Milky Way playing? The universe makes sounds. Now the sounds animals make to see with. Number 3. Echolocation precision. James Simmons, a neuroscientist at Brown University, has spent the better part of his career trying to figure out what a bat is actually doing when it echolocates. In his laboratory in the 1970s and onward, he trained big brown bats, Eptesicus fuscus, to discriminate between targets differing by fractions of a millimeter in distance. The rule from sonar engineering is that resolution is bounded by the wavelength of the signal used. A bat's biosonar pulses sit roughly between 20 and 100 kilohertz, giving wavelengths in air of a few millimeters. Standard theory predicts the bat should not be able to resolve target features finer than that. The bat resolves them anyway. Simmons published in the Journal of the Acoustical Society of America and elsewhere documenting that Eptesicus fuscus can discriminate range differences on the order of 0.3 millimeters, corresponding to arrival time differences of roughly 0.5 microseconds between echoes. Whitlow Au at the University of Hawaii demonstrated comparable performance in bottlenose dolphins in the 1990s using targets suspended in seawater. Cynthia Moss, running the Bat Lab at Johns Hopkins University, has extended this work to dynamic hunting behavior in three-dimensional space. The failure parade covers every attempt at reverse engineering. Simple cross-correlation models of returning echoes predict worse performance than the animals achieve. Neural coincidence detection at the level of individual neurons in the inferior colliculus is faster than expected, but still does not fully close the gap. Coherent processing models, treating the auditory system as if it operates on the phase structure of returning signals rather than just intensity, are competitive but not universally accepted. Engineered sonar systems in submarines and autonomous vehicles have not yet fully matched what a small mammal does in flight while chasing a moth, which means an animal with a brain smaller than a walnut is performing signal processing that a room full of engineers with modern computers has yet to fully replicate. What is the bat's brain doing that ours cannot describe? Bats break the resolution limit. The next one breaks the structures we build. Number 2. Standing wave anomalies in large structures. On the morning of November 7, 1940, engineers monitoring the Tacoma Narrows Bridge in Washington state noticed unusual twisting oscillations in the deck. The bridge had opened 4 months earlier. The wind that morning was moderate, roughly 40 miles per hour. By late morning, the deck was twisting through arcs of 45 degrees. Film footage of the collapse became one of the most viewed engineering documents of the 20th century. The rule the designers had followed was straightforward. Bridges were designed to withstand static wind loads and expected vibrational modes. The dynamic behavior of the Tacoma Narrows deck, however, was not simple resonance in the elementary sense that early textbooks described. Post-collapse analysis over decades has changed the explanation multiple times. The original popular account attributed the failure to resonant forcing of the bridge at its natural frequency by wind gusts. Robert Scanlon, an engineer at Princeton and later Johns Hopkins, argued in a widely cited 1991 paper in the American Journal of Physics that the mechanism was aeroelastic flutter, a self-excited oscillation where the motion of the deck itself modifies the airflow, feeding energy back into the motion. Subsequent modeling has refined this further, and the exact instability class remains discussed in engineering literature. The failure parade extends beyond Tacoma. On its opening weekend in June 2000, the Millennium Bridge in London began swaying laterally under pedestrian foot traffic. Pat Dallard and the engineering team at Arup published on the effect synchronous lateral excitation, where walkers unconsciously adjust their gait to match the bridge's motion, amplifying it. The bridge had to be closed and retrofitted with dampers. Earlier examples run back to the Broughton Suspension Bridge collapse in 1831 under marching soldiers, which means for 2 centuries, engineers have kept building structures where the interaction between the structure, the wind, and the crowd produces oscillations that were not in the original calculations. The buildings and bridges around you are still being audited. What frequency is the ground under your feet already resonating at? Structures we thought we understood. And to close, a sound we thought we understood. Number 1. Sonic boom physics edge cases. Aerodynamicists have understood the basic shape of a sonic boom since the 1950s. When an aircraft crosses the speed of sound, roughly 1,225 kilometers per hour at sea level, it generates shock waves that coalesce into the characteristic N-wave pressure signature on the ground. The physics was worked out in the wake of the X-1 program and refined through the Concorde era. The rule for predicting boom intensity at any given ground location involves aircraft geometry, altitude, speed, and standard atmospheric propagation. Given inputs, the boom on the ground should be predictable. Under most conditions, it is. Under specific conditions, it is not. Kenneth Plotkin, whose work on sonic boom propagation spanned decades at Weil Laboratories and included NASA-funded studies published through the 2000s, documented what are called focus booms and super booms. When an aircraft accelerates through the sound barrier or maneuvers at supersonic speed, the shock waves can converge at specific points on the ground, producing pressure amplitudes several times larger than the standard steady flight boom. Similar focusing occurs from atmospheric refraction. Temperature gradients and wind shear can bend shock waves so that multiple wavefronts arrive simultaneously at a given point. The failure of predictability is well documented. NASA's ongoing work on the X-59 Quest-ST, a low-boom demonstrator aircraft flown in test programs through the 2020s, has been dedicated in part to characterizing the atmospheric variability that makes precise boom prediction difficult. Reviews in IA publications have noted that even with modern computational fluid dynamics and detailed atmospheric modeling, the ground-level boom at any specific location cannot always be predicted within tight bounds. Concorde's over-water routing was mandated in part because the shape of the ground-level signature over land could not be reliably controlled. Which means that for the entire supersonic era, we have flown aircraft producing acoustic events on the ground whose peak intensity at any given house we could not always predict. The sound arriving at your window from a jet overhead is emerging from a physics we understand in outline and cannot always compute in detail. If we cannot predict the sonic boom, what else are we solving in outline? Every entry on this list sits inside physics we have written down, not at the edges. At the center. The bloop was recorded by instruments we built. The Taos hum is heard by ears we've studied for centuries. The bat's sonar operates on principles our textbooks describe. Sound is one of the most familiar phenomena in nature, pressure waves in a medium, and the pressure waves in the medium around you, and inside you, and above you remain, in specific ways, unresolved. The universe is not confused. We are. If you want to see more videos like this, click the video on screen now.